Hey guys, welcome back. This lecture is going to be a really neat lecture. We're kind of in the middle of talking about electromagnetics. We talked about electrostatics in our last lecture, which is the physics of charges that are relatively stationary to one another. But things start to change and we start moving things around. We need to start talking about those physical attributes, and that comes about when we have something called a current or something moving, right? Like a river current. Well, you can also have a current of electrons as well, which brings about some really neat phenomenon. So without further ado, let's just jump right into this because this is really interesting stuff. Probably the best way to kind of analogize how currents operate is to understand how it works, say, in a water pipe system or in a hydraulic system. If you can see it in a hydraulic system, then it makes it a lot simpler to understand how wiring works, for example, or what we call a circuit will work in the real world. So, flow of charge. When the ends of an electrical conductor are at different electrical potentials. Remember from our last lecture, and if you haven't seen it, you need to make sure that you go back and watch that lecture on electrostatics. We talk about electric potentials. And we're going to be doing some review of this, but I'm not going to spend a whole lot of time talking about it because I will have made the assumption that you've watched that film. But when there is a potential difference, charge flows from one end to the other. And this is analogous to water flowing from higher pressure to lower pressure. So if you have an area here of higher pressure, which is, say, a higher potential than this here, it's going to flow and try to even itself out, right? To attain a sustained flow of charge in a conductor, some arrangement must be provided to maintain a difference in potential while charge flows from one end to the other. So in other words, to keep a system like this going, right, this is eventually going to level itself out. How do you keep it going? Well, you need a continuous flow is possible if the difference in water levels, hence the difference in water pressures, is maintained with the use of a pump. So you can keep it going as long as you have a pump down here. And so in this case, if we have a pump pulling the water through here and pushing it out through there, right back in, and circulating the water through, you can maintain this difference in water level from here to here, this potential difference. In this case, this would be gravitational potential energy, but we are actually going to start talking about electrical potential energy, something called, well, we'll come to that momentarily. So just like water in pipes, we actually find a flow of charged particles in substances, mainly in wires and fluids, right? We don't necessarily see a whole lot of movement in rubber or insulators, so we're going to concentrate on these two types of medium. So in metal wires, the conduction electrons are charge carriers that are free to move throughout the atomic lattice. We talked about this a lot in the last lecture. We're just going to kind of go through this really quickly. The protons are bound within the nuclei of the atom. So in that case, we don't really see a flow of protons. We find a flow of electrons, right? The electrons are actually free to move within the metallic bonds, for example, in copper wire. But in fluids, it's a little bit different. Positive ions, called cations, and electrons constitute electric charge flow. So in this case, you can actually have the atom, as long as it's an ionic atom that's positive, it will actually follow the rules that we're describing here as well. We're going to actually concentrate mainly on the stuff in metal wires, but just understand that in fluids, this can be a major component. So the rate of electrical flow is measured in something called amperes. You guys have all heard of amps, right? You know, you turn on your vacuum cleaner and it draws, a 1 amp of current. The speed of electrons, though, what we call the drift speed through a wire, is slow because of continuous bumping of electrons in wire. So one of the things that is a kind of a misconception in dealing with electricity is that we believe that when we turn on the vacuum or the iron or whatever, that the electricity is flowing from the power plant straight into our iron at the speed of light or something close to it. That's not true, actually. In fact, electrons move through wires at extremely slow speeds, about the speed of molasses or honey dripping down a wall. It's actually not very fast at all. So you might be asking yourself, well, then why is it when I turn it on, it goes active right away? We'll get into that shortly over the next couple of lectures. But just understand that it's not necessarily the same, electrons are not necessarily the same thing as energy. The electrons are the medium by which energy is delivered, but not necessarily the energy itself. So charge flows through a circuit. Voltage, however, is established across a circuit, right? So charge is moving through. It's kind of like, think about a river. The charge that flows through a circuit, which is the ampere, is the amount of water that would be in a channel. Whereas the voltage that is established across a circuit is the angle at which the water is flowing downhill. So they're related, very closely related, in fact, yet different phenomena. So you want to make sure that you have an understanding that voltage is the difference in the potential, or it's the potential difference, whereas the charge flows through a circuit. The amperes is kind of like the amount of charge that's moving through. Alternating current is another kind of important idea that we need to think about. We've been talking about how electrons flow through a wire. In an alternating current, they don't necessarily flow as much as they oscillate. So in alternating current, electrons oscillate to and fro about fixed positions, kind of doing this, just sitting there shaking back and forth. Okay. Movement is produced by a generator, at least in how we do it in our artificial wiring systems, in our power grid, or an alternator that switches the signs of change, or signs of charge periodically. So what happens is you have basically a whole lattice of protons. The electrons are moving or flowing one direction, and then they reverse, and then they go back the other way. They just sit there and they move back and forth. Okay. Commercial AC circuits are used in most residential circuits throughout the world and can be stepped up to high voltage for transmission over great distances with small heat losses, or stepped down where energy is consumed. So when you have a high voltage, it's really efficient to transmit in high voltage. When you're doing for power grids, it's useful to do high voltage. But when you want to consume it, that's really difficult for a lot of our appliances to deal with, so you got to step it down. And we'll talk about transformers and how that is done in a couple of lectures. So that's actually a whole lecture on transformers coming. And again, another review, conductors, any material having free electron or free charge particles that easily flow through it when an electric force acts upon them. And the electric potential difference is charges in a conductor flow from higher potential to lower potential. Flow of charge persists until both ends of the conductor reach the same potential. In other words, this is trying to fill it up. Maintained for continuous flow by pumping device. So this is really just kind of a review of what we've been talking about, not just since the beginning of this lecture, but the previous lecture as well. No flow of charge occurs when potential difference is zero. This is the kind of the important part of this slide, is that if you don't have a potential difference, in other words, if you don't have a higher and a lower, there's nothing motivating the flow of either electrons or water or whatever it is that you're talking about to move. If you don't have that potential, it's extremely important. And of course, we also know that potential is in electrical systems called voltage, right? So electric potential differences, we're going to continue this, is usually generated by a battery or a generator. That's usually what does this. The work is done by pulling negative charges apart from positive ones. Electromagnetic induction at the generator terminals provide the electrical pressure, I like that word pressure, to move electrons through the circuit. So just as we have a water pump here pushing things through a valve, the valve is the on and off switch, and then it goes through a line of resistance of some sort, right? So notice how this line is smaller than this one, so it actually kind of backs the water up somewhat, and then it goes back through the pump. You get the same thing actually through a circuit of electricity. You have an electrical circuit. You turn on the switch, the same thing as turning on the valve. You have a resistor here where the wire suddenly gets thin, or for whatever reason, it's more difficult for the electrons to flow through. And what's driving the whole thing? Well, it's basically an electric pump called a battery, right? That's what a battery does, or a generator. In chemical batteries, we get these electric potential differences in a couple of ways, and one of the most common ways is by just putting a Duracell battery that you get from the store. And this is done by the disintegration of zinc or lead in acid. So over time, it releases the chemical, the energy stored in chemical bonds is converted to electric potential energy. Remember, law of conservation of energy. If you can't destroy energy, but it can change form. And in this case, we're just changing chemical to electrical, and we take advantage of that in our Duracell batteries. Use it to power light. And in this case, our light is our resistor. We'll talk about resistors here shortly. Oh, as a matter of fact, very shortly, it's the very next slide. Electrical resistance. Current in a circuit is dependent upon voltage and the electrical resistance in ohms, right? So this makes a lot of sense, right? Here we have a current of water, but what if we put a crimp in it, right? That crimp is actually going to set a upper limit on what our current can be through this pipe, okay? And so resistors in electrical circuits are circuit elements that regulate current inside electrical devices. So resistors are important, right? If you don't have these little crimps, things can get a little crazy inside of your radio or your microwave. Usually when we're drawing these things out, unfortunately, I don't have my stylus. My stylus has been kind of inactive as of late, and I have another one ordered. But anyway, resistors are usually drawn with this little kind of sawtooth pattern right here. And we'll be seeing some of these. As a matter of fact, you saw one right back here. So here we see the switch, and here and these are my wires, of course, coming out of my battery. And here's my resistor here. That's all this is trying to tell you, is that that's what it looks like when we draw them out. Electric resistance, there's several factors that bring this about. First off, inversely proportional to the cross-sectional area. What does that mean? Let's just break that down. Thin wires have more resistance than thick wires, right? Same thing with a water pipe. If you have a thick water pipe, more water can get through with less resistance than if it's thin. There's less friction. I call it electrical friction is how I think of resistance. It's directly proportional to length, right? The longer it is, the more resistance you're going to experience. In this case, doubling the length doubles the resistance, provided that the entire system is consistent. The material is also important. Rubber is much more resistant than copper of the same size, and it turns out that's also a temperature aspect to it. The higher the temperature, the more the resistance. This is one of the reasons why when you first turn on a light bulb, at least the old school light bulbs, the current would start flowing through it. As the filament heated up, the resistance got greater and the light would get brighter. So as time went by, the filament would heat up, the room would actually get brighter over time, not dimmer, not the opposite. And so up here is a photograph of some various different kinds of resistors, ceramic resistors, and so on and so forth that you find in switchboards and things like this. Common, you can go to Radio Shack and you can buy, packs of these, maybe 10 of these for $5. They're common. This is also a review of previous lecture. Semiconductors, these are refer to materials that can alternate between being conductors and insulators. Good ones are germanium and silicon. This is the reason why we find our computer microchips made out of silicon. Germanium is rare. It's extremely expensive relative to silicon, so this is what we generally go with. Superconductors, zero electrical resistance to the flow of charge. Flow of charges without generation of heat. If I'm going through this too fast for you, by all means, I know I've said it several times, I can't hit it hard enough, make sure you watch the previous video on electrostatics where I talk about this in detail. High temperature superconductors refer to ceramic materials that can carry much current at low voltage, right? All right, so I said all that. We kind of worked really hard to get to this one concept right here, and we're going to build on this over the next couple of lectures, but this is probably the most critical one. Ohm's law. Ohm's law is what establishes the relationship between voltage, current, and resistance. It turns out they're all really forms, we can't really have one without the other. And it states that the current in a circuit varies in direct proportion to the potential difference or voltage right? Voltage is the potential difference. And inversely with the resistance. In the equation form, we just simply say the current is equal to the voltage divided by the resistance, where I equals V over R. And remember, the unit of current is the ampere. So we have, this is the number of amps is going to equal the voltage divided by some resistance, which is given in units called ohms. Unfortunately, I don't think I typed that into this PowerPoint, but it's OHM, and it's the Greek capital letter omega. Don't worry about it. You can look it up online, or it possibly will be in your textbook. But anyways, resistance is given in ohms. Examples, for a constant resistance, current will be twice as much for twice the voltage, right? So as long as this stays the same, these are proportional to one another. So if this goes up by a factor of 2, that'll go up by a factor of 2. So you take the same system and you put a battery, instead of a 12-volt battery, you put a 24-volt battery on there, you're going to double the current. For twice the resistance and twice the voltage, the current will be unchanged. So if you put an extra resistor on there, even if you double the voltage, the current won't change. It's just a pretty straightforward relationship. Just make sure that you understand that they are, in fact, all related one to another. And if you happen to have the voltage and the current, you can work out the resistance and vice versa, right? If you have two of them, you can figure out the third. And so when we draw these things, here's our voltage. Our voltage in this case might be a battery or a generator that's producing electrical current. That current is pushing electrons, maybe in a direct current way. We'll be talking about direct current and alternating current here shortly in detail. But there's current coming through, goes through a resistance. Say that resistance is a light bulb. There's a resistor. And that light bulb is yielding power, right? Maybe it's a 60-watt light bulb. Remember, watts is a unit of power. And it's connected through, the electrons are basically trying to make their way to the opposite side. Ohm's law also kind of explains the phenomena of electric shock. So damaging effects of shock result from current passing through the body, right? Your body is not set up to be able to accommodate large amounts of charge moving through you, or current. So electric potential difference between one part of your body and another part of the body depends on the body condition and resistance, which can range from 100 ohms to 500,000 ohms, right? If you have a very large resistance, remember, it's going to play a role in here. A very large resistance here is going to wind up reducing the current that can go through you. But that means that you're going to probably have some problems, right? It just really depends on where it's going to hit you. But all right, so we have direct current and alternating current. We've heard about these terms probably since our childhood. Let's go ahead and illuminate you a little bit on these ideas. First off, direct current flows in one direction only. Maybe you have a battery, and the battery is sending electric charge in one direction along a wire, and it just continues to circulate it around. Electrons always move from the negative terminal towards the positive terminal, right? Always. Remember this. This is almost certainly a concept that you'll need to know for your unit assessment. Alternating current. Electrons in the circuit are moved first in one direction and then in the opposite direction, alternating to and fro about fixed positions. We've talked about this. So here we see two graphs. I'll come to the graphs here in a moment. This is accomplished by alternating the polarity of voltage at the generator or other voltage source. We'll be talking about how these generators in fact do this very thing in a couple of lectures. Anyway, so here's a direct current in time. We'd see that it's going in one direction, whereas if we see the current and over time for alternating current, it's going back and forth in a sine wave, right? Almost changing signs. Here we have it going positive, negative, positive, negative. In this case, it's always going the same direction, right? Electrons always move towards the positive terminal, right? This is where it's going forward, back, forward, back, forward, back. That's alternating current. Commercial electricity in North America is alternating current. There was a big debate between, I believe it was Westinghouse and Thomas Edison and Nikola Tesla, as to what was kind of the best way for the United States to go in terms of establishing its power grid. Ultimately, we established the alternating current system. It actually is a much better system to go with. Um, but you get the idea. There was some early political strife over this. But anyway, so we actually are on the AC system, advocated by Nikola Tesla. 60 cycles per second. In other words, every second that goes by, this goes up and down 60 times. The rest of the world has different values. I believe Europe is at 50. The United States is at 60. Voltage is usually set at about 120 volts. Power transmission is more efficient at higher voltages, however, and that's the reason why Europe adopted the 220 system. The United States is at 120. The U.S. basically continued it because we already had 120 in place. It would be an extremely expensive endeavor to change it. The question is whether or not it would be worth it. There have been a lot of people that think we should do so, but there are ways to fix the voltage problem using transformers and whatever. And the real question is whether or not it's worth the investment to do this for the entire power grid. But anyway, you get the idea. Well, not the entire power grid, but for the local power grid. Cool. So how do you convert from AC to DC? Because, I mean, a lot of us have laptop computers or whatever, and we're not dealing with AC current coming into our computers. We usually work with DC. How do we convert it, right? Because the power plant's producing AC. The power plant is not sitting there sending out electricity, or I'm sorry, not sending out electrons all day long. It's just all its job is to do is to just shake electrons back and forth. That's all it does. Move it back and forth. So household current is AC, but current in laptop is a DC, right? The converter uses something called a diode, which is a tiny electronic device that acts as a one-way valve to allow electron flow in one direction only. So in other words, every time it goes this way, it allows it through, but when it pulls back, it doesn't. It doesn't allow any change to occur. So every time the electricity moves in one direction, it records it. So when we're converting from AC to DC, when the input is to a diode is an AC, output is pulsating DC. So here we see up in this thing here, this is our AC current. 60 cycles per second. And basically the diode is only allowing the positives to come through. Okay, see that? It's basically eliminating the negatives, or it's not letting us see the negatives. Slow charging and discharging of a capacitor. Oh, there's a capacitor. Wait, there's a capacitor in here. I love capacitors. Provides continuous and smoother current. In other words, the capacitor comes in, it hits it, and it charges it. And then it slowly releases it. So we get a pulse in, the capacitor continues the discharge, and then it charges back in, charges back in. In other words, it smooths it out. And if you use a pair of diodes, so a pair of diodes is used, so there are no gaps in current output. Look at this. So if I use two, I can basically take this negative here, and I can flip it to a positive, and then I can smooth it out using capacitors on both of them, and I get this result here, right? So that one here, the positive, this is the old negative, which is now a positive. And as long as I use two capacitors on them, I get this nice, it wavers a little bit, 60 cycles per second, but for the most part, I get a pretty smooth input into my computer, all right, for my laptop to operate, or my cell phone, or whatever it is that I'm using that's using direct current, DC, okay? Here's some, by the way, some pictures of diodes. You can buy them again at Radio Shack, real cheap. Is there anything in here? The pair of diodes reverses the polarity of alternate half cycles instead of eliminating them. Okay, so we've covered that. All right. So let's go back to speed and source of electrons in a circuit. You know, we were talking, I kind of said it earlier that the electrons aren't exactly moving through things at the speed of light. When we flip the light switch on a wall in the circuit, an electric field is established inside the conductor, right? We know this, right? Whenever you have charges, you're going to have an electric field. The electrons continue their random motions while simultaneously being nudged by the electric field. So in other words, the electrons aren't just suddenly sliding all in one direction. Even though I've been showing it like that through a wire. What happens is there's just kind of a slight nudging for them to go kind of on average in a different direction. So for example, in this case, there might be a nudging of this particle, this electrical particle within this apparatus here to move from right to left, right? So originally it starts here, now it's over here. So over time it's being nudged. It doesn't mean it's still not randomly bouncing around and moving over all over the place in a Brownian way throughout the substance. If you don't remember Brownian motion, we covered that about 12 lectures ago. So back when we talked about subatomic or atomic particles, the atomic nature of matter. Current is established through the wires at nearly the speed of light. Wait a minute, you said the electrons don't move at the speed of light, so how can that be? Current is established through the wires at nearly the speed of light. It is not the electrons that move at the speed, it is the electric field that can travel through a circuit at nearly the speed of light. So it's kind of like a train, right? You can go and you can start pushing the caboose on the train, and you might have a mile of cars in front of that train, but if you start pushing the caboose, the front of the train will start moving at almost exactly the same moment. That doesn't mean that the caboose is moving very fast, it just means that the transmission of that force is going to be transmitted throughout that entire train at about the speed of light. It's going to be very, very fast. Okay? That is basically what is being stated here, is that the electrons might not move, but the energy that they convey is at about the speed of light. Okay? So there's a couple little things we need to bring up. If the voltage source is direct current, like a battery, electric field lines are maintained in one direction in the conductor. So here we see, here's the positive terminal, here's the negative, here's the electric field lines moving about. Conduction electrons are accelerated by the field in a direction parallel to the field lines. Okay, so in other words, if you have an electron in a wire, it's going to move through parallel to this field line right here. Before they gain appreciable speed, they bump into the anchored metallic ions in their paths and transfer some of their kinetic energy to them. So as a consequence, things kind of start to move around, right? So you get a lot of transference, you even get heat, a lot of things start to happen. So you just need to be aware that not all things move as fluidly as we think, right? You know, these electrons aren't in superhighways in metal wire. They're running into things and it slows them down. So that allows us to start answering some of the misconceptions about electric current. So current is propagated through the conducting wires by electrons bumping into one another. That's not true. Electrons that are free to move in a conductor are accelerated by the electric field impressed upon them, right? Okay, they're not propagated by electrons bumping into one another. True, they do bump into one another and other atoms, but this slows them down and offers resistance to their motion. It doesn't actually speed things up. It doesn't cause things to propagate. If anything, it works against them. Electrons throughout the entire closed path of a circuit all react simultaneously to the electric field. It just moves through at the speed of light. Okay, it has nothing to do with the electrons bumping into one another. It has everything to do with the emission of an electric field about the circuit. Okay. Here's another misconception. Electrical outlets in the walls of homes are a source of electrons. That's not true either. The outlets in homes are alternating current. They're AC. Electrons make no net migration through a wire in an AC circuit, right? We're just talking about how they just move back and forth. They alternate back and forth. When you plug a lamp into an outlet, energy flows from the outlet into the lamp, not electrons, right? Energy does, right? Energy is carried by the pulsating electric field and causes vibratory motion. Electric utility companies sell energy, but you have to provide your own electrons, right? And that's actually what this huge generator, this is a large generator in China, very large generator in China, is producing electricity. And basically what it's doing is this huge apparatus is just sitting there pulling and tugging, pushing and tugging back and forth, jerking electrons back and forth all over the area that this Chinese power plant serves. So you get the idea here, and we'll talk about electrical generation, like I said, in a couple of short lectures. We have to talk about magnetism first before we can explain it. So what does that mean electric power is? Well, electric power is the rate at which electric energy is converted into another form. In equation form, power is equal to current times voltage. So there's voltage again. We know the current, we can figure out the power, and that gives us the watts. right? So it turns out if you actually know the voltage of your how would you say it? If you know the voltage of your light bulb, maybe, or I'm sorry, of your wiring in your house, which is usually about 120 volts, and you know the power, say 60 watts, you can actually figure out the current. You can kind of figure it out right away if you think about it. I'm not going to give you the answer. Think it through. If you can't come up with it, send me an email. So the units for that are watts. Power is always in watts. So this again is another power generating system. There's some apparatuses here, some transformers. We'll be talking about them again shortly. All right, so what does this mean for how we live our lives? Well, incandescent bulbs are the bulbs that have existed for a very long time. They're the old school bulbs with the kind of the light filament that goes through it. As a matter of fact, I had a picture of a series of them. That's these right here. These are incandescent bulbs. There's some problems with them, and that is that they actually radiate most of their energy across that resistor. That filament is actually a resistor. It releases heat, a lot of heat, but not a whole lot of light. So they're not very energy efficient. We want something that's going to actually release a lot of light, not a lot of heat. And it turns out that fluorescent lamps emit much less heat, which is why you can touch them without burning yourself, right? You can take one out and plug it in or whatever, it's not going to get you. CFLs, which are compact fluorescent lamps, are a type of fluorescent lamp that fits into a standard light bulb socket. This is what they look like. I have to confess that I have these all over my home now. As I record them, I'm actually under 2 of such bulbs, and they are not the most attractive bulbs to have in your light fixtures. So there's a give and take on these things. But anyway, for the same wattage, CFLs emit much more light and much less heat than incandescent bulbs. So in terms of their light, they're very efficient. Okay, they're not very good looking in your light apparatus, so you have to have a nice lampshade or some way to cover them up, unfortunately. Another light source that's even more long-lasting is the LED, the light-emitting diode. This has been invented in the last, 10, 15 years, something like that. The most primitive being the little red lights that tell you whether your stereo is on or off, right? If there's power going through it, it lights up. And so it tells you that if it's electrically live or not. So between CFLs and LEDs, common use incandescent bulbs will soon be history. And in fact, I believe, if I know the law correctly, I might not, but incandescent bulbs are essentially outlawed. You can't purchase them anymore at the store, or if you can, it's very difficult to acquire them. I don't know the details about all of that, but anyway, right now CFLs and LEDs are kind of what's available to you. So that leads us to electrical circuits. We've been kind of hinting at them and without really talking about them directly. We've talked about the Ohm's law, which kind of implies the existence of electrical circuits. So let's talk about them. So it's any path along which electrons can flow from the negative terminal to the positive terminal, right? Remember, this also happens in fluids, right? You can have ions that do this that are positively charged, but we're going to just stick to wires. Wires are a lot easier. Complete circuits allow continuous flow of electrons with no openings or gaps. So remember, we're talking about water, you got your pump, no openings or gaps, and we're basically circulating this stuff around. In this case here, our pump is our voltage source, a battery, and we have a flow of electrons going from the negative terminal to the positive terminal. And so we can connect circuits in 2 different ways, right? So there's basically the series circuit, which forms a single pathway for electron flow between the terminals of the battery generator or wall outlet. So here we have this would in fact be a series circuit. Here we have the battery, here's our switch, and we have 2 lamps, which are resistors, right? And they just are not that different than any other resistor you would see, whether they be lamps or cell phone or laptop plugged into your wall. But anyways, it's all connected to the same circuit. That's the idea. So there's a 12-volt battery, and we see them in series. They're both on the same line. But in parallel, basically you're forming branches, each of which is a separate path for the flow of the electrons. So here we actually have a battery plugged in. This is another way that we can symbolize a battery. This is a little more abstract than this one. But here's a battery. So as we have the circuit on, we actually see a series of resistors that are set up in series. But over here, notice you can take a path through resistor 3 and avoid resistor 4. And in doing so, you have a parallel circuit here, and you have a series circuit on the same thing here. Okay, so there's two different ways you can connect things in a circuit. And there's consequences for this, right? So the consequence, or the characteristics of a series circuit is the electric current through a single pathway, right? It's pretty simple, right? Here's a battery, here's 3 lights, you throw the switch and it works, right? It's all in one thing. But what if you cut the battery right here, or cut the line right here, and the whole thing goes dead? Total resistance to current is the sum of the individual resistances. So you add up all the resistance, and that's the amount of resistance on the entire system. The current is equal to the voltage supplied by the source divided by the total resistance of the circuit, right? That's Ohm's law. Just using Ohm's law, you can figure out the current. Total voltage impressed across the series circuit divides among the individual electric devices in the circuit. So the sum of the voltage drops across the resistance of each individual device is equal to the total voltage supplied by the source. In other words, it all adds up in the end. The voltage drop across each device are proportional to its resistance. All right? If one device fails, current in the entire circuit ceases, right? Because you cut the circuit. Right? If this bulb goes out, that filament goes out, it severs the entire line and we lose our circuit. Conversely, we have parallel circuits. And so we can set this up so if you can cut one line, the other ones will still work. But it does mean that the physics is a lot different. So voltage is the same across each device. So here we have it set up in parallel. Notice this comes in here, and then it splits it off. It branches it off into different switches that go through different lights. In this case, this switch is off, these two are on, and so these two work, and this one is off, right? So in other words, if I don't have to have just one switch to run all 3, I can have different switches, and you get it. You know, it's a little bit more convenient, but it's also a little bit more complicated. The total current in the circuit divides among the parallel branches. The amount of current in each branch is inversely proportional to the resistance of the branch. The total current in the circuit equals the sum of the currents in its parallel branches, all right? So this is going to get this is slightly different than we were just talking about, right? As the number of parallel branches is increased, the overall resistance of the circuit is decreased. So in other words, it's almost like opening the pipe up. So as you open up more switches, as you open up more lines that are in parallel, the resistance drops pretty fast, actually. A break in one path does not interrupt the flow of charge in the other path. So this might seem to have a lot of advantages, and in fact, parallel circuits do have a lot of advantages over series circuits for specific tasks. For example, wiring a house. Almost all houses are wired in parallel circuits. But the fact is that without a lot of resistance, you can get a lot of current flowing through things, and things can get out of control, and you wind up with things like fire hazards. So parallel circuits tend to overload as a consequence. Homes are wired in parallel. As more and more devices are connected to a circuit, more current moves through the wires, right? Because the resistance drops. There is an amount of current each device can carry before it overheats. When the current is excessive, overheating can result in a fire. That's how you get electrical fires in your house. Also, the addition of excess devices in a parallel circuit increases the amount of current moving through the wires, right? Producing an overload and overheating of the system. And that can result in a fire, right? So there's a couple of different things you can do that really cause problems. And so this winds up being the consequence here. You have an electrical fire that's taking down this unfortunate house. So we can devise different techniques to get around our problems. And one of them is we can develop safety fuses. Safety fuses are simply wires that melt when the given current is exceeded. So you can make a wire that can only take so many electrons going through it over any given period of time, so many amps of current. When that is exceeded, it basically melts and that breaks or severs the circuit, right? It kills the circuit. These are usually connected in series along the supply line to prevent overloading in circuits. So you want to make sure that you're careful about that. and they're replaced by circuit breakers in modern buildings, right? So the cool thing is if there's a circuit breaker, if you exceed the proper amperage, you can go and throw the switch and you can turn everything back on. In the old days, you used to actually have a fuse in there, and the fuse would blow out. You'd have to actually have one from the store. You have to put a new fuse in. I actually remember my grandmother put an old nickel in there to keep it going. Of course, that takes away all the safety value of the circuit breaker in the first place, but you get the idea. Circuit breaker is simply an automatic switch that turns off when the current is excessive. So in this case here, we have a safety fuse. Here we have a current coming through. There's a fuse ribbon that goes through to the circuit, and if you exceed it, you basically blow out the ribbon, and that shuts everything off. So that's your safety aspect. Anyway, so you got the idea. The main things that you want to make sure you pull out of this is Ohm's law, the relationship between these things, and understand what a resistor is. Resistor is really just a spot on a circuit where we use the electrical current to do work or to produce power. And if you understand that, that I equals voltage over, or current equals voltage, which is given in volts, over resistance, which is given in ohms, you can do a lot of really powerful calculations with that. And you'll be doing some of that in the homework sets. So anyways, I think I've talked long enough about this stuff. I think you kind of get the idea. If you have any questions, send me an email, meet me on the discussion board. Don't want you to be confused. In the meantime, have a good one. We'll talk to you next time.